All right, Math 158, section 1.2. This section is called Functions and Models. And we're going to just, in this section, all we're going to really do is get an idea of what do we mean when we say a function. I believe I've said this in previous videos and previous lessons, that really what a function is it's a rule that it's a mathematical equation where for each input, there's only one output. For each value of x, there could only be one value for y. So basically in this section, we're going to talk about functions. We're going to talk about modeling. What do I mean by a mathematical model? What I mean by a mathematical model, or what we say when we say mathematical model, is it's an equation that represents a real life situation. So look at example 1. Okay, so for your 10th birthday, your grandparents gave you $200 to begin saving for college. Because you don't know anything about saving, all right, a little word missing there. Because you don't know anything about saving, you keep the money in a box in your bedroom. So you don't know anything about banking, you don't know anything about interest. We'll talk about that later in the course, but you decide to keep your money in a box in your bedroom. Each year on your birthday, your grandparents give you another $100, and you put it in the box. Just after your 18th birthday, you're preparing for college. How much money will you have in the box? Okay, so let me come over here to the side and talk about ways to write equations, okay? So in an algebra class, you might be taught y equals mx plus b. Excuse me, where m represents the slope, okay? Slope can also be called the rate of change. And the b represents the initial value, okay? And you can write the equation like that, but there's nothing that says it has to be y equals mx plus b. So I have a number of times with students seen them write y equals b plus mx. And they write the initial value first, because in a lot of times that does actually make sense. Okay, and I don't really care. I mean, you might be more comfortable with the y equals mx plus b, where we're told that has to be in standard form, the normal form, the appropriate form, right? But if you write a b plus mx, it's not going to really make that much difference. Okay, now remember that this problem, and I'm going to go back and forth here, right? For your 10th birthday, your grandparents gave you $200 to begin saving for college. And because you don't know anything about saving, you decide to keep the money in a box, right? So each year they're going to give you another $100. So let's make a table here. On your 10th, let's not put that there. Let's put, this is your birthday. Let's call it B. And this is the amount of money that you have total. Okay. So on your 10th birthday, when you turn 10, they're going to, I guess maybe let's not use B there. Let's use X, right? How old are you? So on your 10th birthday, your grandparents give you $200. On your 11th birthday, you still have that $200, but they give you another $100. On your 12th birthday, you still have the $200 and the $100 they gave you on your 11th birthday. Now you're also going to add to that another $100. On your 13th birthday, and I'm trusting you're all smart enough to see the pattern by now, on your 13th birthday, you still have the original $200 you got on your 10th birthday, plus the $100 from your 11th, the $100 from your 12th, and now a third $100 gift on your 13th birthday. And notice what's happening here is that the initial value, 200, is still there. You were only given that $200 once. So you had an initial gift of $200. Then you got $100 on the 11th, 12th, 13th birthday. So what I could do is that's 200 plus 100x. So y, the amount of money I'm going to have in that box, is $200, the initial value, plus $100 each year after that. Now it's also going to be important that you write, remember, notice what x represents. X does not represent your age. X doesn't represent the year 2010, 2015, 2020, 2021. It doesn't represent any of those things. X represents the number of years after your 10th birthday. So for your 11th birthday, X is 1. For your 12th birthday, X is 2. For your 15th birthday, X will be, that's right, X will be 5. Okay, so Y, the amount of money in your box, is 200 plus 100X. This is what I'm saying about writing it in the Y equals B plus MX format. Now, the correct way to write it would be Y equals 100X plus 200, but I think sometimes in an application setting, 200 plus 100X makes just as much sense. So back to example 1, right? So we just did the equation. So for your 10th birthday, your grandparents, I'll be okay, your grandparents gave you $200, then $100 on each subsequent birthday. Okay. Just after your 18th birthday, remember that X is years since your 10th birthday, and abbreviate birthday. Okay, so on your 18th birthday, X would equal 8. It's the 8th birthday after your 10th birthday. So the amount of money, and really, since this is a function, we can replace the Y with F of X. So F, the amount of money, when X is 8, after your 8th birthday, after your 10th birthday, or after your 18th birthday, is 200 plus 100 times 8, or 200 plus 800, you would have $1,000. Okay? Don't spend all that money in one place on college. Right? I'll buy you a little bit, but then you would have $1,000 in the box, and you're going to say thank you very much to Grandma and Grandpa. Okay. Number 10 is a little bit different. Okay. For your 10th birthday, your grandparents just gave you $1,000. Rather than giving you $200 on your 10th birthday and $100 each subsequent year, your grandparents instead are just going to give you $1,000 upfront. Bam, there you go. But you do know something about saving, so you're going to invest the money into an account paying 8% interest, compounded monthly. Just after your 18th birthday, you're preparing for college. How much money will you have in the account? Now, setting this up, doing the work, this is all going to be Unit 3. This is the type of problem that we're really going to hammer out in Unit 3 because the entire course has to do with functions. But just to set this up here, to give you an example of what we mean by function and modeling, okay? So your grandparents are going to give you $200. Now, let's assume for a moment that your interest is compounded annually, once a year, not once a month. Each year, you're going to multiply by 1.08. The reason for that 1.08 is let me take it again, and a little wander over here to the left and talk about interest and things, right? So let's suppose that you have a job and you're making $50,000 a year. And you work for me. I know that's really kind of scary, but you work for me, and I decide, you know what, I'm really going to reward you guys this year. You worked really hard, and so I'm going to give you a raise of 10%. I'm going to give you a 10% raise. How much money will you make? What will your new salary be? What a lot of people will do is say, well, what we're going to do is we're going to find 10% of 50,000, which is 0.10 times 50,000, which is 5,000, and we're going to add that to the original $50,000. And so 5,000 plus the 50,000, right? Here's 50,000 plus the 5,000. Your new salary would be $55,000. I know that you had done that far ahead of me. But if you look here, this is where I want you to look. We could factor out 50,000. And if we factor out that 50,000, this 50,000 divided by 50,000 is 1. 0.10 times 50,000 is 0.10, and that would be 1.10 times the 50,000, or 50,000 times the 1.10. It's this here that I want to pay some attention to. I believe that most people, by the time they get to this point in their education, are okay with 50% equals 0.50. 72% is equal to 0.72. But what about 110%? That would be 1.10. So really what this means is you're going to have 100% of your 50,000 plus 10% more. Okay. So let's bring this back over here and think about it this way. You're going to keep that $200, and each year you're going to have 100% of that original amount plus 8% more. Okay. And X is again going to represent the number of years after or since your 10th birthday. So on your 15th birthday, X will be 5. On your 16th birthday, X will be 6. Okay. And let's again replace the Y with f of X. Now this would be if our interest is compounded annually, where we're getting 8% interest per month. If your interest is going to be compounded monthly, you're going to have that 100% plus each month you get 1/12 of the 8%. So that function would be 200 times 1 plus 0.08 over 12 to the X. Okay, I hope that makes some sense. Now, in problem number 1, just after your 18th birthday, how much money will you have in your account? 200, 100 times 8 is 800, plus 200 is 1,000. That's not too hard to do, okay? To say, well, what about after my 18th birthday, just after my 18th birthday, how much money will be in the account? Let's suppose that we want to, what if we compounded our interest annually? That would be f of 18 is equal to 200 times 1.08, not to the 18th, but to the 8th. And so this would not be f of 18, this would be f of 8, since X is the number of years since my 10th birthday. My 18th birthday is 8 years after my 10th birthday. So on my calculator, this is not going to be too hard. Notice I have my calculator here on the right. Yes, you are going to want to have a graphing calculator. 200 times 1.08, close that parenthesis, and then we need the exponent button, which is right here, to the 8th. So if the interest is only compounded annually once a year, oh, nope, sorry, I made another mistake, didn't I? Because they didn't give us 200 to start with, they gave us the 1,000. I apologize for that. So this should not be 200. That should be 1,000. So let's do this again. 1,000 times 1.08 to the 8th. Okay, that's better. So after 8 years, after my 18th birthday, I would have $1,850.93. Notice, by the way, the dollar sign comes in front of the number. That would be if the interest is compounded annually. However, if the interest is compounded monthly, we're going to use this formula. Okay, we're going to use that one. And in that case, f of 8, right, 18th birthday, 8 years after my 10th birthday, is the original 1,000 times 1 plus 0.08 over 12, not to the 8th, okay? Okay, it's going to be number of months because this is monthly. So that would be 8 times 12 because that would be 12 months. 8 years, 12 months per year is actually 96 months. So this one, 1,000 times 1 plus 0.08 over 12, close the parenthesis, to the, there's my exponent again, and right here, 8 times 12, the calculator will handle that 8 times 12 in the exponent, and you actually make an extra $42. Okay, so that would be 1892 46. Okay, so there's an example of using functions to model a situation. And that's what we're going to be doing in this course is we're going to be using functions to model real world scenarios. My experience, by the way, with students has been, you're teaching them some algebra, you're teaching them some math concepts. Well, when am I ever going to use this? When am I ever going to use this? And you start pulling out problems like these, and somebody says, oh, I don't like doing word problems. I don't like doing application problems. And well, that's kind of where this stuff gets used, right? Okay. So, number one, number two, you could look at that comparison and say, hey, grandma and grandpa, if you're going to give me $1,000 over the next 8 years, what if you just gave it to me now when I can collect interest? And it almost doubles in that time frame. Now, you all know what the issue with that is, right? Maybe they don't have the full $1,000 right now. Okay. So, number three, suppose, and I don't know who typed this stuff. Suppose that I have 120 feet of fence and I need to enclose a rectangular garden. Write a model of the area of the garden as a function of its width. Okay. Now, big thing you need to get right here, write a model for the area as a function of the width. If I write y equals 3x plus 6, I've written y as a function of x. Okay, I've written y as a function of x. So what you'll notice is that to write something as a function, to write the area as a function of the width, we're going to have the area equals something with w in it. So garden, let's make the garden green because they should be, right? So here's my garden. Let's say that this is the width of the garden and this is the length of the garden. We all know that area, I hope we all know, that area is width times length. Now I've written the area as a function of the width times the length, but this says to write the area as a function of its width only. Okay. Now we're also told we have 120 feet of fence. This length is W. What happened there? This length is W, L, so this is also W, so this is L. So we should all know that 2W plus 2L is 120. If we divide both sides, divide everything by 2, we get W plus L is equal to 60. So I can solve this for L. See, now I've written L as a function of width. So let's take that 60 minus W, and we're going to substitute that in for the L. And so the area is width times 60 minus width. Now notice I've written the area as a function of the width. The one last thing I could do if I want to is write A with the parenthesis with the width. That means area as a function of width is equal to the width times 60 minus the width. And there we go. That's area expressed as a function of the width. Okay. Now, something else that we want to talk about here, right? The cost of renting tuxes, right? So here's another example of where we're going to use functions or use an equation to model a situation, to describe a situation. Okay. So really modeling is writing a mathematical equation and using that to express, in this case, the cost as a function of X. Okay. We're renting tuxedos. How much does it cost to rent a tuxedo? Okay. So some terms that we're going to look at, right, will include, you can look ahead to D, E, and F here. The things that we're going to look at are variable cost, fixed cost, marginal cost. Okay. And really the fixed cost and the marginal cost are, I think, where we're going to struggle the most. Okay. Now let's just talk through this. The cost of renting tuxes for the Choral Society's formula is $20 down plus $88 per tux. Express the cost as a function of X, where X is the number of tuxedos rented. I'd like to believe that this is not going to be too difficult to say that the cost for renting X tuxes is going to be $20 plus $88 per tux. Okay. That initial cost, that $20 down, keep this in mind, that's an initial cost. In fact, what is the fixed cost? The fixed cost is $20. I'm going to pay $20. That $20 does not get me a tux. That $20, all that it gets for me is the ability to rent tuxes. It's a cover charge, if you will. So I'm going to go to the tuxedo place and I say, hey, I got these 10 people here with me that are all going to rent the tux. And I say to the vendor, I say to the person working there, what does it cost to rent a tux? And the person working there says, well, for each of them, it's going to cost each one of them $88 to rent a tux. So the first one of you will cost $88. The next one, it'll cost you $88. The third one will cost you $88. There's a pattern here in case you haven't caught on. Okay. The cost of the second tux, this is not, well, every once in a while. Okay, this is not the cost of renting two tuxes. B here is not the cost of renting two tuxes. It's the cost of the second tux. It costs $88 to rent the first tux. It costs $88 to rent the second tux. It costs $88 to rent the third tux. It costs $88 to rent the fifth tux. It costs $88 to rent the 10th tux. Okay. But when I go into the store and I say to this person, I need to rent tuxes, what will it cost? And the guy says, well, what you're going to need to do is you're going to create an account. Is it going to cost me anything? Yes, he says, it's going to cost you $20 to create that account, and then each person that rents a tux will cost them $88. Okay, so the cost per tux is $88. That, by the way, is the marginal cost. That changes. Okay, that's the marginal cost. The variable cost is simply 88x. Okay. If you're used to y equals mx plus b, or I've written this one y equals b plus mx, if you're used to the fact that m is the slope and slope is rate of change, that's the rate at which the cost of renting tuxes is changing. That's my marginal cost. The variable cost, notice, is that term with the 88x. Okay, the fixed cost is that b, that initial value. Okay, I hope I've said this enough, and we'll do some more of these as we go through the course. So let's look at Amazon here, right? The following table shows some annual revenues in billions of dollars earned by Amazon from 2004 through 2014. And we can talk about Amazon, and they've been in the news a lot lately too. But this is their revenue in billions of dollars. In 2004, okay, their revenue was $7 billion. In 2006, their revenue was $11 billion. In 2008 was $19 billion, and so on. And the question here is, would a linear model be best to represent the change in Amazon's annual revenue? And the answer is no. It would not be. Well, why not? What is it about a linear model that's different from any other model? And I'm going to look back to number 4. You see this marginal cost? It's $88 per tux. To rent 0 tuxes will cost me $28. If I want to rent one tux, it's another $88. For the second tux, it's another $88. For the third tux, it's another $88. For the fourth tux, it's another $88. For the fifth, it's another $88, and so on. Each additional tux costs the same. My cost of renting these tuxes is going to increase by $88 for each additional tux. That's a linear model. So you'll notice that in the 2-year period from 2004 to 2006, Amazon's revenue increased by $4 billion. In the 2-year period from 2006 to 2008, their revenues increased by $8 billion, and then $15 billion, and then $27 billion, and then $28 billion. So what you'll notice is that the rate of increase is not constant. The rate of increase is not a consistent amount. So it is not a perfect linear model. A linear model would not be the best because the rate of increase is changing. Okay? Because the rate of increase is changing, and that's why that linear model is not the best. Okay? So last couple concepts here. It's going to seem a little disjointed, but I think it's not too bad. Okay. Sometimes we're going to take two functions and we're going to write them together. So all we're going to do here is practice in this video. How do I write the sum of two functions? To find the sum of f plus g of x. To find the sum of two functions, you add them together. To find the difference of two functions, you subtract them. To find the product of two functions, you would multiply, and the quotient of two functions, you would divide. So one quick example here, f plus g of x. I'm simply going to add f of x plus g of x. Okay, that's all I'm going to do. F of x is x squared plus 3x minus 5 plus g of x, which is 3x minus 2. And now I'm simply going to combine my like terms, x squared plus the 3x is 6x, minus 5 and minus 2 is negative 7. F plus g of x equals, and there you go. Now you'll notice I've written this as an equation. You have to have an equation. Every year when I teach, every semester when I teach this course, I will have students that will give me this answer and think that it should be okay. And I'm going to tell them it's not okay because I'm asking you for a function. Find the function f plus g of x. A function has to be an equation, okay? So this is no good. It must be a function. There's got to be an equation, f plus g of x equals. So B. To find the difference of the two functions, I'm simply going to subtract them. So that's f of x. I'm just going to use, for all four of these, A, B, C, and D, I'm just going to use the same f and g. So f of x minus g of x. So again, combining like terms, we have an x squared, 3x minus 3x, those cancel. Negative 5 minus negative 2 is negative 3. So f minus g of x equals negative 3. Okay. To find the product, f times g of x, I'm simply going to multiply f of x times g of x. So that's x squared plus 3x minus 5 times 3x minus 2. Okay, and we did this previous video expanding this, and I'm going to choose to take the 3x times x squared, 3x times 3x, right? That's 9x squared. 3x times negative 5 is a negative 15x, and now the negative 2 gets distributed to everything. Negative 2x squared minus 6x plus 10. We combine our like terms. I've got the x cubed term. Now I've got 9x squared and a negative 2x squared is 7x squared. The negative 15x and negative 6x is a negative 21x. And then now we have plus 10. And that's our f times g of x. Okay, so there's the product of two functions. Lastly, we have the quotient of the two functions. Now this one, really, a lot of people don't like it because, oh no, I have to do f of x divided by g of x. But really, f divided by g of x is simply going to be f of x, 3x squared plus 3x minus 5. Whoops, nope, it's not 3x squared, just x squared plus 3x minus 5 divided by 3x minus 2, and you're done. except that we now have, because of this denominator here, we now have a restriction on the domain that x cannot be 2/3. And that's because the 3x minus 2 cannot be 0. So 3x cannot be 2. So x cannot be 2/3. So I need to include that new restriction on my domain. Okay. So that's section 1.2. I hope I wasn't rushing too much near the end. You saw the alert come up that my pen battery is dying. So we'll take care of that here in a second. But what we're doing is working with functions, getting used to working with functions. Make sure that you look at the problems that are in WebAssign and that you practice those. Okay. And if you have questions, please drop by my office hours or shoot me an email. Thank you.